Alright, continuing in 10.1, we're now up to example 7. We are talking about infinite series and sequences of partial sums at this point. And so, example 7, and they've got a good demonstration in the textbook about chopping something in half and in half and in half and in half, and take a look at that when it's not actually an example. But it says consider in number 7 this infinite series, 0.9 plus 0.09 plus 0.009 plus 0.0009 plus ... where each term of the sum is 1/10 of the previous term. Find the sum of the first 1, 2, 3, 4, 5 terms of the sequence. Okay, well the sum of the first 1 terms is just 0.9. The sum of the first 2 terms would be 0.9 plus 0.09, which would be 0.99. The sum of the first 3 terms, okay, I think I see what's happening here, 0.999. They want 5 terms. 4 is 0.99999, and 5, 0.99999, because I just keep adding the next term. Part B, what value would you assign to the infinite series? Oh, well the infinite series appears to be approaching 1, because I keep adding a 9. So for this was part A. For part B, I would say that as n gets, well not as n, as the term numbers get larger to infinity, the sum of the n terms would be approaching 1. Now we have a formula for that, for summations, and it is in your book, but I want to pick out the most important parts of this. Before I give you the formula, if I just go back to that S sub n, it would be 0.9 plus 0.09 plus 0.009 plus ... all the way out to, and that would be the sum of 9 times 1/10, we'll call it a k, as k goes from 1 to n. So if I'm summing up the n terms, I would start with 9 and I would multiply it times 1/10 all the way up. Now, there are several ways of writing this, but then we could just say that it approaches, and we would say the limit, as n approaches infinity, of this sum, k equals 1 to n of 9 times 0.1 to the k, is approaching 1. So that's what we're doing with that. And so they've given us a formula down there that says if you have a summation and it has terms that you can see it's approaching a limit, then this is how you write it. Now, if the sequence of partial sums diverges, then the infinite series also diverges. So let's look at example 8. And it wants the summation k equals 1 to infinity 1 over k times k plus 1. Find the first 4 terms of the sequence of partial sums. Okay, so the sum of the first 1 term would be 1 over 1 plus 1 times 2 is 2. The sum of the first 2 terms would be 1/2 plus, now I stick a 2 in there and I get 1 over 2 times 3, which is 6. If I add that together, I get 2/3. The sum of the first 3, I would take the 2/3 and add the third term to it, which would be 1 over 3 times 4, which is 12. And that gives me 3/4. If I sum up the 4 terms, I start with 3/4 and I add to it, stick in 4. 1 over 4 times 5 is 20. That gives me 4/5. If I look at these partial sums, it appears to me that this is approaching 1. Now, there are some little rules that they haven't given us before, but what's happening here is you have a rule for summations that says the sum of the n terms of a sequence is the first term, and I like to write it as a sub 1, over 1 minus r if it's a geometric series. So in this case, In this case, it's not geometric, so that one won't work. So we're trying to come up with another one that would make this work. So let's think about this for a minute. When I'm on the first term, I had a 1 on top and a 2 on the bottom. When I got to the second term, I had a 2 on top and a 3 on the bottom. So the numerator appears to be the actual number of terms you've added up. Because S sub 4, it's a 4 on top. And the number underneath the denominator is always 1 higher. So I could say this turns into n over n plus 1 for n equal 1, 2, 3, and so on. Now, what I'm doing then in that case, if I'm doing this analytically, I'm taking the limit as n goes to infinity of n over n plus 1, which we've learned previously. The degree on top and bottom is the same. The answer is 1. Or if I used L'Hopital on this, I would say the derivative of the numerator is 1, the derivative of the denominator is 1, and I would still get 1. So I can look at my sums and make a conjecture on it, or if I can turn it into an equation that would work, I can take the limit of it that way. And this concludes section 10.1.